Welcome to the final installment of Fun with 4. That is with layer 4, the transport layer. In this video, we will look at the problem caused by congestion and how TCP addresses it. The specific problem that we will talk about is known as congestive collapse. It is where the network becomes so congested that it effectively becomes unusable. We will also review what we've discussed about TCP to see what we have learned about the transport layer in general. Finally, we will discuss the second example of a transport layer that we promised to discuss in some detail, UDP. The final challenge that TCP has to address is that of congestion. In fact, as we said a moment ago, the problem is congestive collapse. It is when the network becomes so congested that it becomes unusable. TCP uses two techniques to deal with this. The first technique is slow start. And the second technique is exponential backoff. We're going to look at slow start now, which you will soon enough see is a bit of a misnomer. What you have on this graph, on the x-axis, you have the round trip time. So that's some estimate of how long it takes for a packet to be sent out and to be acknowledged. On the y-axis, you have a value n, 1, 2, 3, 4, and so on, and n is multiplied by the maximum segment length. Maximum segment length needs some explanation. So in TCP, packets are not really called packets. It's not wrong to call them packets, but it's better to use the correct term, which is segments. So the maximum length of a segment in bytes is the maximum segment length. And when we multiply the maximum segment length by some factor like 2 or 3 or 4, that gives us something that is known as the congestion window. The congestion window should not be confused with a window at the receiving side of a TCP connection. The congestion window is positioned at the sender, not at the recipient, whereas the flow control window is positioned at the recipient. So this one has nothing to do with available buffer space or anything like that. How it works will become clear in a moment or two. Now, what happens is that TCP will start sending a small number of packets initially, a small number of segments. So let's say that initially the sender is allowed to transmit one packet. The moment that single packet is acknowledged, it says, now I am allowed to transmit 2 packets. When those 2 packets are acknowledged, when the one is acknowledged, it adds 1. When the other one is acknowledged, it adds another one. And in other words, for both of those, it will be allowed to send additional packets. So at this point, it is allowed to transmit 4 packets. When those 4 packets are acknowledged, then it adds another 4 to the number of packets that may be sent out. And what you can see here is that it is doubling the number of packets that may be sent out. Now, I've been using the word packets here because what it actually means is the number of bytes that can be transmitted if you multiply the number of acknowledgements n with a maximum segment length. That gives you the congestion window, and that would give you the bytes that it is allowed to transmit. Somewhat easier in this case to talk about packets. At some point, there will be some threshold determined, and then this is predetermined. Let's say that the threshold happens to be 8. Technically, this is known as the single start threshold, and if you look at the technical literature, you will very often see that they talk about SS thresh to indicate the slow start threshold. If you look at what we've had thus far, you will see that we've had exponential growth. Now, the moment that it hits this threshold, it does not allow another packet to be added in each case. It simply monitors the next RTT, the round trip time, and if acknowledgements are received, then it just simply adds 1 to the number of packets that may be sent. So it doesn't count the number of packets that are acknowledged. It doesn't count the number of acknowledgements for segments. It simply says we got acknowledgements. And then during the next time period, the next round trip time period, it again, if packets are acknowledged, it adds 1 to the window, and the same is true for what happens after this. So what this means is once the threshold has been reached, the increase in the window size becomes linear. Suppose that we've reached this point, let's say at that point is the last point at which we received positive acknowledgements. What will happen now, or what may happen now, is that some packet is lost. And TCP assumes that it is lost because of congestion. And TCP does 2 things. The one thing is the threshold that used to be 8 is typically halved. So the new threshold becomes 4. The other thing that happens, and this does depend on the version of Unix on which you are working or from which your system was derived, may restart the slow start process. In other words, it may reset it to 1. So what this would mean is that the system is now allowed to send out 1 segment again. If that is successfully acknowledged, it may send out 2. If those 2 are successfully acknowledged, then for both of them we add 1 to the number n that is multiplied by the maximum segment size to give us the congestion window. And you can again see that we've got this exponential growth curve. But we've reached the new threshold. So from this point onwards, whenever during a round trip time period, a single packet or any number of acknowledgements is received, doesn't matter how many, we just add 1 to the window size. So this window size, when I say add 1 times the maximum segment size or maximum segment length. So at that point, growth becomes linear again. If we lose another packet, then we're going to restart the segment or the window at 1, and we're going to halve the window, that threshold again. And so it will continue. Now, as I said, this is one variant that does this. There are other variants where once something goes wrong, for example, where that first packet was lost, it will not go back to slow start. It would rather go back to the window size. In fact, not that window size. It will halve the window size, as we said earlier, so the same there. But then from that point onwards, it will immediately go into the linear increase. So no slow start exponential process. It will immediately go to this linear growth. So exactly how this works does depend on the specific implementation. A lot of research is being done on this topic. So it's hard to talk about TCP, how it works in practice, but it uses this idea that we've seen here, that it typically halves the threshold. It uses a slow start process to get to the threshold and then grows linearly from there, with at least one major variant that when a packet is lost, only halves the threshold and then skips the slow start and uses the linear increase from there on. The second mechanism that TCP uses for congestion control is exponential backoff. It's worth noting here that TCP is not the only protocol that uses exponential backoff, but this is a good place to discuss it. Recall that TCP segments that are sent out have to be acknowledged. And if they are not acknowledged within a certain time period, then TCP will have a timer that will expire and the segments will be retransmitted. So in the technical literature, very often the abbreviation RTO is used to indicate the retransmit timeout. So that's the duration that a TCP sender will wait before it retransmits a packet. Initially, that may be set to something like 200 milliseconds. So what we had in our previous discussion of events, we had something like this, where for some packet I, the retransmit timer expired. And what we said was we just enable we just retransmit packet number I with its acknowledgement and so on. And we also said that the retransmit timer for I is simply activated again. But the truth is slightly different. Rather than just reactivating it, what happens is we take the RTO, the retransmit timeout, and we double it. So the old value that we would have waited before we would have said that it's time to retransmit it, we double it, and at that point we start the timer for I again. The logic of this is that, to make life simple, let's say you've waited a minute for a packet and it's lost. Then if you immediately retransmit it and the problem is indeed congestion, then you're just adding to the problem by keeping on retransmitting. So what you're doing is you're waiting longer and longer and longer before you attempt to retransmit lost packets. In that way, at the very least, you're not adding to the problem. you're slowing down your attempts at rectifying the problem with retransmitting it. Now, at some point, typically at about 9 minutes or so, TCP will say it's no longer worth trying, and it will tell you that the connection has failed. So a lot of research being done, many questions that are being asked whether this exponential backoff is indeed still necessary, because we are using much faster networks than in the old days. A lot of implementations will try and figure out whether this packet was indeed lost due to congestion or for some other reason. Some of the mechanisms that they employ is that if a recipient, for example, gets one segment, misses one, and then gets another one, then it will only be able to acknowledge the first one, because TCP acknowledges everything up to a certain point. So when this recipient gets segments, let's call them segment 1 and 3, even though they are numbered in terms of bytes, if this recipient gets number 1 and 3, it will know that 2 has been lost, but 3 came back successfully, and it will acknowledge number 1 multiple times. And then the transmitter will say, okay, number 1 got through successfully, but this station on the other end is trying to tell me something by keeping on acknowledging it. And at that point, it will say, oh, let's just quickly try and retransmit it, rather than going into this back-off procedure. So lots of questions, but in the standard implementation, the standard way in which TCP was conceptualized, it at least very soon after it was conceptualized, and they run into this problem of congestive collapse. They started implementing it with the exponential backoff. So technically it is still part of TCP, even though a lot of questions are being asked about it. What we're going to do now is to look at the TCP header. So recall that you will get your information from the upper layers. It will arrive at the TCP layer. The TCP layer will use whatever came from the upper layers as payload, and then it will add its own header. When we talk about the header, it seems like something that you've got to memorize. It looks like something that deserves a lot of parrot repeating work. And the point that I'm going to make now is that no, that's not the way you should think about it. You should be able to think about what goes into that header based on what we've already said thus far. So very briefly, it means your packet is sent. There back at the end is the payload. And what we are interested in is what's going in this header. So let's only talk about the header. And you know that the transport layer in general is used to connect two processes. So somehow you have to identify the process at the destination end. And that is done using a simple number, and for whatever reason the word port was used to refer to that number. So at the destination end, the process will be identified by a number, a port number. So we will have a destination port in this header. If the destination wants to respond, it needs to know what the number of the process is on this machine that we are sending from. So we will also have a source port in the header. Clearly, based on what we've been saying about the reliability, you will have a sequence number to indicate what the payload is, at what byte number, at what byte position it starts. In the same way, you will have an acknowledgement number to indicate what is being acknowledged, what is the next byte that you expect. You will have a length to say how long is this packet that you are sending, how many bytes or how many octets does it contain. Also, remember that we spoke about the window advertisement. So somehow we will have to tell the other party what is the size of our available window. This is not the congestion window that we spoke about earlier. This is the window in which we will place incoming traffic. And finally, we will have a couple of flags. And those flags will be flags like SYN. Remember, for the handshake where you send a SYN message, that is simply a bit position in the flags field. And in the same way, if you wanted to say goodbye, you would say fin. And again, that is simply a byte or a bit in the flags field. There's also an ACK bit to say that you're acknowledging something. So perhaps to make matters clear, we have to make it clear that that ACK field is the acknowledgement number, and the ACK bit indicates that we are acknowledging something. And then there are a couple of other flags that we will look at right now. So this leaves us with a little bit of a challenge, obviously. If we want to know exactly where in the header are these fields packed in, or where do they fit, what goes into the first little bit and what goes into the second bit and what goes into the third piece of that header, well, my response is, if you need that information, you just look it up in the manual. It's much more important for you to have knowledge of what goes into that header field, rather than exactly where they fit in. If you, as I said, when you need that, you look it up in the manual. Here we are looking at an example of what the TCP header actually looks like. Just quickly reading it from the top left-hand side, you will see that there is the source port that we mentioned, there's the destination port that we mentioned, there's the sequence number, there's the acknowledgement number, then there's a data offset field that we didn't talk about, we're not going to worry about that. There's a reserved field that we're not going to talk about. And then we get to the flags field. Now the flags field, those values should be read from the top to the bottom. So the first flag field is URG, urgent. It's when you want to send an urgent message. We're not going to talk about that. There's the ACK field that you use for acknowledgement, as we said earlier. There's the PSH, which is push. We're not going to talk about that. There's the RST, reset. We're not going to talk about that. There's the SYN field that we already talked about. There's the FIN field that we already talked about. So the three important flags there, ACK, SYN, and FIN. Then what is labeled window is the window advertisement. The checksum is a checksum across the entire TCP segment. So if anything is changed accidentally in the TCP segment, the checksum will change. Then there's an urgent pointer options and padding that we're not going to talk about, and then the actual data, the payload that came from above. So this brings us to the end of our discussion of TCP. Clearly, there's a lot of things that we skipped over and that we said it's not important for our purposes. So there's a lot of room for you to study TCP in much more depth if one day you want to. Moving on to the second example protocol that we want to talk about, UDP. That's the User Datagram Protocol. So UDP is a connection list protocol. It does not set up the connection as TCP does. We compared it to the postal system earlier, where you simply send a message out and you hope for the best. Why would anyone want to use such an unreliable protocol? And again, unreliable with a specific meaning that we've assigned to it here. If something goes wrong, we won't know about it because no sequence number, there's nothing to acknowledge it. If it's lost, it's just simply lost. Let's think about one or two scenarios. One scenario is DNS name resolution. Recall that for DNS name resolution, you basically want to send a name to a DNS server and you hope to get an address back from the DNS server. So if you were to use TCP for that communication, you would use the hello and the goodbye, the three-way handshake on both sides. So the communication would be, I want to talk to you. Okay, let's talk. Yes, let's talk. And then this machine will say, will you translate this for me to an address, please? And the server will say, this is the address that you're looking for. And then this machine will say, goodbye. And that one will say, goodbye. And this one will say, yes, that's really it. We've sent 8 messages to and fro. And only 2 of them were really important. The one that asked, will you do this lookup for me? And then the response. What's more, with DNS, you already know that there are primary and secondary name servers. So if the primary name server doesn't work, you're going to ask the secondary name server. So the error control or error correction is arguably much better than asking the same server again and again and again and again and hoping it will answer, because you're just going, if the primary doesn't provide you with an answer, you're going to ask the secondary server. So the sequence here will simply be something where you ask the message, please resolve this name for me, and then if you get a response back with this is the address, that's fine, it worked. If you don't get an answer back, well, maybe you're going to try it once more with the same server, but then you're going to move on to the second server. You're going to ask the secondary server, maybe even the tertiary server, if the secondary server doesn't answer. And one of them will answer. And if they don't, it probably means the network's broken anyway, and it's time to give up. So you don't need all that overhead to try and repeatedly ask the primary server. It's much better to move on to the secondary name servers. Now, there's something that we should note here. DNS name servers also do zone transfers. The primary server takes its entire zone at some point and transfers everything to the secondary zone or the secondary server, so that the secondary server is indeed able to resolve queries. Now, to send that large block or potentially large block of names and addresses, it will use TCP. So it's not true that the DNS uses UDP full stop. The truth is the DNS uses UDP for name resolution, these quick queries, but it uses TCP for zone transfers that entail this transfer of an entire block where you do not want something to go wrong. As a second example, why you may prefer something that does not have all the reliability of TCP, think of voice communications. Something like VoIP or some protocol where you are using the network to communicate in a telephone-like manner. So in this telephone-like manner, If you were using TCP, it may miss a millisecond of speed, of sound. And then it's going to stop this entire transmission. It's going to say, retransmit that millisecond of sound for me, put it into the right place, and then it's going to transmit the rest. You can just imagine if this were to happen time and again while you're busy talking to someone on the phone, where it stops and then maybe waits a couple of seconds and then it continues. It's much better for this to be transmitted at fast speed. And if every once in a while you miss a millisecond of sound, your ear will complete that word. You don't need every millisecond. So here TCP's automatic repeat request nature will work against you. It's better to lose a little bit of data and your mind will fill the blanks and it's good enough. It's not like a financial transaction where missing a couple of million rand will suddenly cause major problems. So let's look at the header of a UDP datagram. And just a reminder that UDP packets are typically called datagrams. They're sort of like telegrams, like something you put in the mail and they get delivered somewhere. So while we can talk about UDP packets, it's better to talk about a datagram. So this datagram has the same structure that we've seen all over the place. Whatever comes from the top is the payload, and that gets into the body of the datagram. And what we are interested in right now is what goes into the header. What is added by UDP as the header field. Now, again, UDP, just like TCP, has to identify the processes that are communicating. So there will yet again be a destination port and there will be a source port. They will indicate where this message starts, or rather where it originates from, and where it's going to, so that the recipient can respond to this by just inverting the destination and the source. What else needs to be added here is a bit of a challenge, because if you begin to think about what we added in the previous case, there was a sequence number. With UDP, there's no notion of sequence. There's no sequence number. There was an acknowledgement number. Here, we're not acknowledging anything. There was a length. Yeah, okay, that makes sense. So we need a length. We had a window size that we advertised when we established the connection. Here, we are not establishing the connection or anything. So it's almost what we have. There's very little else to add. Okay, one giveaway. We will add a checksum, which was perhaps not clear earlier, but this checksum will actually just be over the header. It will not be about over the entire datagram. So even if data is changed in the datagram, UDP won't care. It will just go ahead and deliver, because even if something goes wrong, there's no way that it can ask for a retransmission. There's no acknowledgement. That's it. So here we have the formal layout of a UDP datagram. You can see the source port, the destination port, the length, and the checksum, and then the payload that makes up the entire datagram. Very little we can add to that. So you basically know everything about UDP that you need to know. As is so often the case, the only way you can really get a feeling for how these protocols work is to look at them in action. So what I have here is a Wireshark capture I opened a session using my web browser to a server. I've included a remark in that green line, not a remark, a filter in that green line at the top where I said IP address is equal to the address of the server I connected to, and you can see the entire conversation there. Again, it's hard to get this detail into a font that is large enough while retaining everything of interest where you can really expect to read it on your screen. But what you will see if your resolution is good enough is that the first line is a TCP segment that has been sent out, and you can see the SYN flag is set. And then the second line is also is a response actually from the server where SYN plus ACK is set. And what we would have expected in the third line is something from our machine out to the server again that just acknowledges it. It's not the case. And this is what makes a lovely examination question. Why is it not the case? What happened there? And the only way in which you'd be able to answer that is to actively go and play with Wireshark and look at packets, create situations such as opening a web page on some foreign server, and then inspecting the traffic that you've caught or that you've captured between you and that server. Just want to point out again that in the second pane of TCP, or of Wireshark rather, you can see all the protocols that are in use. And in this particular case, TCP has been used. I opened it up so you can see, if the resolution is good enough, you can see what the values of the flags and the various fields are. One of the interesting things that you may discover is that the length of that initial hello is 1, not 0. And that's a phantom byte, what they call it. It's not really a byte that's transmitted, but the acknowledgement counter goes from 0 to 1 during that handshake. So go and play with these protocols. Look very carefully. You can clearly see what the lengths of the segments are, and you can see what is being acknowledged, and you can go and check whether you are able to reconstruct the communication to figure out why the fields have the values they have. Go and play. That's the way you'll get to learn about this protocol, these protocols on layer 4.
Music on this